Okay, let's get started. So, welcome to the April Facts webinar. What we're going to be looking at today is more stuff outside of facts than within facts, and we're going to be looking at how do we optimize a trial that we're trying to design in facts. And certainly the first part of the talk, I'm going to be using work that's being done with us at Lancaster University by Matt Darlington and Luke Rhodes-Leader. It's being coordinated and instigated indeed by our colleague Peter Jacko, previously of Lancaster University, now a Berry Consultants, although still keeping a toehold at Lancaster. And so I had the pleasure of actually in the first part of the talk presenting other people's work. So the problem, as I think anyone who's used facts to design trials will know, is that for most of the types of trials that you can design in facts, there's quite a large number of options and quite a large number of parameters whose values you can vary. And simulating any one particular design, any one particular selections of options and particular values of those parameters over a range of scenarios of interest can take some time. And of course, it will only yield slightly approximate estimates of the operating characteristics because of the stochastic nature of simulation. And we've potentially got quite a number of different dimensions and values we would want to explore in trying to optimize our trial design. And typically we use a combination of simulation and experience, I should say, and to efficiently explore the design space. And we're normally content to find a good design rather than necessarily the best. But what if you're a new user, you've only just started to use facts to design trials or simulation in general to design trials? How do you start to get this experience and learn to and be comfortable with the design choices you've made? It would be nice if we could convey experience, but actually it requires quite a lot of time from senior people. Every trial's design setting is different, and it's hard to extract from them rules that are universal. And we thought, well, instead of trying to put together sort of teaching on optimization of design, which we might do at some point, we could alternatively, or we could supplement it with exploring some options to automate the process, and we draw on some machine learning techniques. And that's what we've started this project with Lancaster University to look at. And our difficulty is that we need to evaluate a design at any particular point we're interested in this space of design options. We need to run the simulations and get operating characteristics, and the results are noisy. So some techniques require that they can cope with you having an expensive evaluation function, but they expect a sort of a precise number out of the end, or they rely on you be able to take a first or second order differential of the function and do gradient stuff. But Bayesian optimization is an approach where to optimize the objective functions, they're for optimizing objective functions that can take a long time, minutes or hours to evaluate. And they tolerate stochastic noise in the function evaluation. So this is kind of exactly the problem we have. And they're well suited for optimizing over continuous domains and less than 20 dimensions. We can probably keep our problem space down to less than 20. Not all our domains are continuous. we'll look at, we'll discuss at some point how we'll might handle that. So the first part of the talk is going to show some early results in this application of Bayesian optimization to a fax trial. And the second, we're going to look at a much more tactical problem rather than the grand strategy of optimization, but one that's of quite a lot of interest, I think, and one that we'll need to have an answer to as part of being able to run an optimization process, which is how do we set the early stopping bounds for a Bayesian design using Bayesian criteria. So those will be the two sort of quite distinct parts of this talk. So starting with Bayesian optimization. So we have some function f of x, and x is our parameter of our vector of parameters, and f is the utility function or the benefit function that we're trying to optimize. We're trying to find values of x that maximizes our value of f of x. Each of the parameters in x, each of the x sub I, is assumed to be continuous and have a bounded range. And we'll need to tweak things where the inputs are not continuous and they're quite discrete. For instance, you might have a design where you're exploring a small number of having some interims, and maybe you want to explore having 1 or 2 or 3 or maybe at most 4 interims. So it's hardly a continuous range. Fortunately, the process assumes that f of x is expensive to evaluate, and it can allow the results have got some stochastic noise. It's also importantly, f of x is assumed to be a black box. There are no derivatives available, ruling out these other optimization methods that depend on the differentials, the gradient descent, Newtonian, quasi-Newtonian. It's assumed that this function is continuous and that smoothing between the evaluated points is a Gaussian process. So it is a reason, using a Gaussian process is a reasonable approach. And I think for almost all we're looking at, well, I think for everything we're looking at here, that's a reasonable assumption. So we're going to try and take advantage of the relative smoothness of this surface, that f, which is the value of f in this multidimensional space. And our approach is we're developing some Python code. A lot of machine learning is available as Python packages, so we're going to take advantage of that. We'll write code. We've already written some code that will take an initial fax file as your sort of starting point design, and then it will be able to vary parameter values automatically inside the fax file in order to create slightly different versions or run it at different points in the space. Complicated modifications of the fax file, such as changing the number of interims, which requires not only changing that, but changing other values as well and making sure that they're a little bit complicated, and they'll possibly remain as a manual change. So the problem I mentioned on the previous slide, where we don't have a continuous range to range over, so in the number of interims, what I think we will do is separately optimize the 1 interim design, the 2 interim design, the 3 interim design, the 4 interim design, and then look at the optimal version of each, and then decide between those 4 which we prefer. So we will take an approach like that. And what the Python code does is it runs fax in command line mode. So it passes fax command line, the fax file it wants simulating, it just runs it, and then it gets the results and is able to evaluate them. There's a nice feature in fax command line mode, which you, as well as the option to give it a file, you can also give it a directory which has a number of files in it, and then it will will simply simulate all those files, so that if at some point we can do things in a parallel way, that will speed up the process. because we'll only be starting facts once. And as I'm sure if you've used facts, as I'm sure you're aware, its startup time is actually quite a few seconds, and could be quite an overhead in this process if we're doing that for every point which we wish to simulate and get some results. So there's a number of questions we still don't know the answer to for sure yet. So one is, can we frame our design question sufficiently clearly that it can be explored automatically, either over all of the design space, or at least a useful chunk of it, so that we narrow down the space which we which we still have to search by hand. Can we summarize our simulation results into a single value, this f function, so it has a single value to maximize? And that might be harder, and it might require trading off a number of operating characteristics, and that might be difficult to get consensus on. And of course, the fundamental one, can the design space, or what size of the design space, can be explored in a reasonable time? It's very unlikely that a single optimization, a round of optimization will get us to where we want, because we'll end up have a design. We'll take a look at that quotes optimal design, and it's quite likely when that's reviewed with the team that things will emerge, opinions or facts or requirements that you weren't aware of when you set up the original optimization. So you're gonna have to go around again. A bit like the iterative loop of using simulation with a clinical team. So the project's in very early days yet, but I thought it's quite interesting to see where we've got so far. And we've kept the examples very simple, partly so we can validate the basic code for things like writing facts files and running facts and interpreting the results. And also we can compare some machine learning approaches. And also, of course, we want to be able to walk before we run. So our very first example was quite trivial. It was to find the sample size, which gives us 90% power for a simple 2-arm trial. And the advantage of that, of course, is we know what the correct answer is, so we can see whether it's doing anything like the right kind of thing. But the nice thing is, once you've got a framework like this, it's actually quite easy to extend it to more interesting problems. So, for instance, we've tried it on a design which it's still a fixed, at this point, it's still a fixed trial, but it's evaluating 6 doses versus control, fitting a 4-parameter sigmoid over a number of scenarios. And the question is, well, what's the minimum sample size we need to have a 50% probability of correctly selecting some minimal efficacious dose? So we'll have a quick look at how it's performed on those 2 examples. So this is the setup for the first example. It's a 2-arm fixed trial with a continuous endpoint. The response on the control is 3 points, and our alternate scenario is a response on treatment of 4 points, so a 1-point difference with a standard deviation of 3. We require time on error to be controlled at 0.025, and we require a power of 0.9. The analysis will be a simple t-test, and of course we can calculate the answer to this. We don't need simulation. This is so we can actually test our simulation and our optimization. And the correct answer is 190 per arm, or a sample size of 380. So we started by running facts over quite a big search space. So we ran 10 simulations in the range of 25 per arm to 500 per arm, or 50 to 950 total sample size. And just how quickly, how many the questions we had in mind was, what did the optimization process look like? How reliably did it find the correct sample size? How many simulations did it require to run at every sample size it wanted to evaluate? So we have these 10 equally spaced intervals, which we simulate first, just running 100 simulations at each. And then we added simulations sequentially at points guided by the Bayesian optimization using this thing they call the acquisition function. In this case, the acquisition function is an estimate of the expected improvement at that point over the current maximum. And we looked at running 100 simulations each time, or 1,000 simulations each time, and 3 different degrees of smoothing in the Gaussian process between the points where simulations have been run. So this smoothing, this process is very like the NDLM model in FACS, and the first one we'll look at is a first order, and the second one we'll see as a second order. We also tried third order. So this is low smoothing, just 100 simulations per point. And this is after the first step of running these simulations at these 10 points. And this is this orange area is the 95% confidence interval. And you can see it's quite unsmooth. The points narrow quite considerably where simulation data is available, and then it's quite uncertain up until the next point. The blue line here is the mean prediction through those points, and green is the true value of the function. So the value of the function is it's based on the absolute difference in power in the simulations at that point from 90%. So here the power is too low. Here it would be spot on, and then here is the power is too high. So, but obviously, as we're looking for power of 90%, that can't differ by that much. But the power is too high. The sample size is larger than we require. And then we have, this is the corresponding value of the acquisition function. You can see the humps where there's the corresponding to the uncertainty, but they diminish as they're less and less likely to give us improvement over our current point. The green vertical bar tells us where the true maximum would be, the 380 subjects, and the red is telling us where the acquisition function is telling us the most useful place to run the next simulation. And on this graph, the red vertical bar shows us the current max. So what its current choice would be. And then we've run 20 simulations. We've allowed it to progress over 20 iterations. And I'll show this. So we have one here now. And you can see there's a little bit of a dimple in the acquisition function. And as we progress, you can see there's more and more points clustered around in the right area. And you can see the acquisition function sort of flattening the value of the acquisition function at that point as it learns more and more about it, but leaving some out here where it's now going to kind of step away a bit from where it's mainly interested to deal with this point, which is perhaps a little less promising than where it has been, but where it currently has less information. So it's run some simulations over here, and now it steps back. And you can see this process repeating it. Every now and again, it'll return to the area where the maximum is, and then every now and again it'll step away to a point where there isn't a maximum, but there is a lot of uncertainty. And round about iteration 17 or 18, things have settled down quite a lot. And the nice thing is that each one of those points, it was only 100 simulations. So the whole sample size is achieved with a total of about 3,000 simulations. So simple problem, but it is going to be addressed pretty quickly. So I'll step in sort of slightly larger steps now. in steps of 5 iterations, but this is with a greater smoothing between the points. And you can see here, given we know this is a pretty smooth surface, this kind of makes more sense, I think. And you have a much more a much better modal value in the acquisition function. It's quite clearly going to stay in round about the right place and not hop off around so much. And indeed, you can see by iteration 15, it's well grouped here. It's going to step away a little bit to one side, but by 20, it's pretty close. What we haven't done is look at some sort of stopping rule. But we've seen with the smoothing, the iterations are more closely clustered around the true maximum. There's a slightly quicker convergence. The uncertainty looks more reasonable. Even higher smoothing might over smooth, particularly if you smooth too much, it's going to miss out where it's actually going to make the peak unlikely compared to the where is mean. But when we go to much higher dimensions, maybe we will want a greater degree of smoothing. I'm not going to show the results, but running 1,000 simulations at each point made hardly any improvement at all. Certainly not nearly enough improvement to warrant the much longer runtime. And the other thing, but we also haven't looked to see whether we could use even fewer simulations than 100. We might need to if some of the spaces we end up exploring have got many dimensions. So this is our more complex example. It's the 7-arm fixed trial, continuous endpoint. Response on control is 0, and we've got a response on the treatment arms, which is sigmoid across the doses, with a maximum response of around about 1 point, a standard deviation of 1 point. And I've created these 6 scenarios by sort of manually playing with parameters to a 4-parameter sigmoid, giving me our target MTD is, by the way, is an improvement of 0.8 over the control. So it was giving me, I set them up to give me MTDs at a range of doses across the scenarios, with 2 scenarios for dose 5, one which was the second one a lot steeper than the first one. So that's what the various scenarios look like, and the required MTD is along this line here. This is a phase 2, so the time and error requirements we can take to be somewhat relaxed, so perhaps around 0.075. Our analysis will be a Bayesian fit of a 4-parameter sigmoid. The objective, as I said, is to find the minimum dose with a response of 0.8 better than control. Our allocation will, at this point, is going to be very simple, just equal allocation across the doses. And our treatment success will be if the Bayesian posterior probability that the treatment effect at the dose selected as the MED is greater than control is greater than 0.9. And that gives us roughly the time and error control we require. And so the task for the optimizer is what's the sample size that ensures that the minimum probability of correctly selecting the MED is at least 50% on averaged across all the scenarios. And in order to find out what the true answer was, we ran a very fine-grained set of simulations. This took several hours to run, running 10,000 simulations basically at every 7-patient interval in the sample size. So 7 patients because we've got 7 arms, so each step represented 1 more subject on each arm. We stopped running them quite so frequently after 600 because it looked clear that the answer was getting very flat. So the upper part of the curve here is interpolated over fewer points. So again, we convert this to a score similar to the first sample size one. So our target is 0.5. So we take the absolute difference between the observed average probability of finding the MED and 0.5 and subtract that from 1. So that gives us a nice set of scores in the range 0.5 to 1. Obviously, we could scale that differently, but it would just be a linear difference. It wouldn't make any appreciable difference. And some of these packages are going to want the function score to lie in the range 0 to 1 anyway. So there's the peak. It's around about 270 subjects. That's zooming in on the peak level. You can see it's about 266 actually, but you can see we've got some stochastic noise in here, even with 10,000 simulations per point. So we've got two optimization experiments on this. One using the method that we've just shown you, and another uses a different machine learning package called the BowTorch. And again, we're running facts just for 100 simulations per point. So this is the reusing the first method, still with our medium smoothing, and you can see that all our values, of course, are above 0.5. And there's quite our first point is a little bit away from the true mean. And then we end up looking something like this. It's still quite a way, even after the first 10 iterations. And you can see we've got a few dotted around quite a way off the distance from the true mean. But then now, after 20 iterations, we're quite clearly homing in on the right value. Oops, and that was where that one finished. So a little bit off the true target. And then with the BowTorch package, which uses a different acquisition function, I think, called the knowledge gradient, that has sprinkled extra simulations quite over the space, but it has the nice property that it even though it hasn't allocated many near here, it's homing in on the correct maximum. And now it's beginning to allocate the iterations on the kind of the flanks of the maximum. We haven't got much closer at this point. Oops, sorry, overshot. But over time, primarily allocating either side. Strangely, not actually at the peak. It does a very good job. So as I said, we have the knowledge gradient. This has the nice feature that it is capable of suggesting multiple points in parallel, so that we can use the facts command line, simulate all the files in a directory feature, and it's quite likely to be more useful in a multi-dimensional optimization. It's got this odd characteristic of simulating on the slopes near the maximum, not the maximum. But of course, it was very easy to add a simulation at the maximum to the set that needed running at any time. So you might have a couple of questions here. One is, well, why does it plateau at 60%? Why can't we make the determination of the MEDs any better than that? And I think it's because the true MTDs in the scenarios I created were all extremely close to the target of 0.8. And typically the dose below it would have a response of about 0.5, 0.6, and the dose above with a response of about 0.88 to 0.93. And even with large sample sizes, it's hard to remove the probability that the dose with the true treatment effect of 0.8 appears to have a treatment effect slightly below that, and hence it chooses the next dose as the MED. So, and indeed, that's the case. If you run it with, say, something like 700 subjects, so 100 on each arm, it's picking the right MED about 50% of the time, and almost all the rest of the time, it's picking the next dose up. So that's what it, but it's almost impossible with larger sample sizes, no matter how big, to do any better than that. So it might have been better to create slightly more random scenarios, perhaps sampling from distributions on the parameters of the 4-parameter sigmoid. It might also be better to have had a more nuanced score rather than simply have you found the MED, maybe penalizing selection of doses below the MED, depending on how far below the response compared to control, how much below 0.8 they are, maybe sort of zeroing out at 0.7, and penalize choices of doses with a response that's greater than the MED dose by the number of dose levels higher, that they are higher than necessary. So maybe we could have scored 1 for being the MED, score 0 for doses with a response less than 0.7, which would actually be, in my scenarios, would have been all of the ones below MED, and maybe score 0.5 for being 1 dose above the true MED, and maybe 0 for any dose above that. So something like that might have been a little better. So we plugged a sample size, not quite the found one. I put in 280, so it was a nice 40 per arm, and simulated that. And interestingly, this was its proportion of times in each scenario that it picked the correct MED. So you can see the actual probability of success was extremely high. The power is, if you ignore the dose selection, is essentially 1 in all, across the scenarios. But actually, you can see there's one scenario where it was much easier to find the MED because there was no higher dose. And so it found it with a probability of 95% roughly, and all the rest are slightly below 50%. And in fact, that you might imagine when the team see that, they think, oh, that's actually, the average might have been good, but when we look at the individual and the chances in some scenarios of being as low as 30%, that maybe this isn't powerful enough. Maybe we need more than 280. So the sample size we think worked very nicely. It can be deployed on any design. So this could have been, could have included response adaptive randomization, arm dropping, anything like that. And we could still ask the question, what's the ideal sample size? We can target things other than power, such as ability to find the correct dose. But it's always important to check the results of the selected optimum, apparent optimum, to properly understand the operating characteristics that are resulted, and maybe that will cause the optimization to be re-examined and maybe the setting tweaked. So we want to move now in next. I haven't got any more results to show you from this, but the area we're going next, of course, is to go to sort of more multi-dimensional optimization. So looking at group sequential and the Bayesian equivalent, the Bayesian Goldilocks design, where we'll be looking, well, what's the optimal boundary for early stopping? What's the optimal number and timing of the interims? And of course, what is it we're trying to optimize? We might take the second example with the 6 doses control and the 4-parameter sigmoid fit, and allow it to vary the 1-to-1 allocation, which will take us towards something like the optimal design. And then we could look at other, if we have time, we might look at other more complex examples, for instance, are featuring arm dropping, response adaptive randomization, or maybe dose escalation. So when we get to doing the Bayesian Goldilocks, the Bayesian group sequential type design, we're going to need some way of setting the stopping boundaries. Now, for the group sequential, we're going to call out to an R package like GS design to return the early success and futility thresholds using these parameterized boundaries, which allow the boundaries to be selected by changing just one parameter to select a particular boundary from a family of stopping boundaries. We're going to use the quite popular Huang-Shi-Dekani family for alpha and beta spending, which is the recommended default in the GS design R package. For a FACS design, could we do something similar? We can't calculate it. And if we can't do something similar, we might have too many degrees of freedom if we're trying to optimize the setting of each of the stopping threshold at each interim separately. And of course, there's the problem that the effects will be correlated, and we need to exclude choices that didn't preserve the type 1 error. And that there's a risk that this makes the optimization process very inefficient. So I wanted to come up with some way of replicating this Huang-Shi-Dekani alpha spending rules in FACS. So design boundaries using alpha and beta spending requires us to estimate what proportion of the trials will stop for early success in a null scenario and early futility in some selected alternate scenario, or possibly averaged for a number of alternate scenarios. And we can do this by simulating the design with interims, but without any early stopping, and ensuring that FACS writes out the weeks files for each one. So we can then simply sort the values of the quantity of interest that'll be tested and find the critical threshold that'll mean we have the desired fraction of errors at each interim. So suppose we've got an alpha spending design that allows us to spend 0.001 of our alpha at the first interim and 0.002 at the second interim. So we run 10,000 simulations of the null scenario, getting FACS to write out 10,000 weeks files. We aggregate the results so that all the weeks files are collected into a single file, and we load that into R. And then from that large data frame, we extract the rows that correspond to interim 1, because these weeks files have a row per interim, and we have a weeks file per simulation. So we extract the rows corresponding to interim 1 for the scenario that we're interested in this case, the null. And we want to extract the columns of the corresponding quantity we're interested in, for instance, a p-value. And then we sort the quantities of these p-values at the first interim, and we say, well, if we have an alpha spend of 0.001 and 10, we've got looking at 10,000 simulations, that means that would be the equivalent of allowing 10 of these simulations to stop for success. So we look at the p-values at the 10th and 11th, the 10th and 11th smallest p-values at that interim. We select a critical boundary partway between them, and so that's going to be our critical boundary. And obviously, with 10,000 simulations, and we're looking at just the first 10, there's a little bit of an error. And this is what the 10, this is an example plot of 10 p-values from exactly such a setting. You can see it's nearly, the underlying data truth is probably linear. And we're going to pick something between the 10th, actually that's the 10th and the 11th as our cutoff value. It'll be a little bit approximate. And if there was only one interim, then it'd be better to run and analyze probably a larger number of simulations. And it's certainly it's quite possible to do with 100,000. The processing takes a few minutes, but it's by no means impossible. But if there are multiple interims and we're going to round the thresholds a little bit conservatively, actually it turns out not to be necessary to worry too much about this approximation. It all kind of comes out in the wash. After all, what we're concerned about is only the overall type 1 error. We're not actually too concerned if the type 1 error at the first interim is 0.001. It might be 0.0009. And the second interim, instead of it being 0.002, it might be 0.0021. That actually doesn't bother us too much. And of course, once we've done this for the first interim, we remove from the data we're looking at these simulations with the 10 lowest p-values, because of course, those simulations will have already stopped. And so we don't include the p-values from those simulations at the second interim when we repeat the process to look at the cut point for the second interim. So, in effect, actually, what we're doing is simply doing via simulation what the group sequential designs do via nested integration. Granted, we're doing it with slightly less precision, but as I said, the overall aim is to control type 1 error and have a more or less aggressive stopping boundary. We're not actually concerned whether we have exactly this 0.001 type 1 error spend at the first interim. And what we gain, of course, is much greater flexibility in this method. We can apply exactly the same code and routine to a multiple arm, which is maybe doing arm dropping, could even be doing RAR, as well as a straightforward Bayesian Goldilocks design, which is just two arm kind of Bayesian equivalent of a group sequential. So let's see how much time I've got left. Quarter of an hour. We might have to fly a little bit through this. So comparing a group sequential to a Bayesian Goldilocks design, let's say we've got a continuous endpoint which is available at 12 weeks for each patient, a standard deviation of 3. And again, we want power for 90% for a 1-point improvement and type 1 error controlled at 0.025. And we're going to use 3 equally spaced interims. We're not going to, at this point, we're not interested in optimizing the number or the timing of the interims. We're just looking at the boundaries. And because we want to ensure we have a method for setting the boundaries straightforwardly rather than having to iterate over them too much. So GS design defaults to this Huangshi-Dikani set of family of boundaries, and it suggests the default parameters for the family should be -2. Oh, sorry, that should be -2 for success. So -4 for success, which is an approximation of the O'Brien-Fleming, and that should say -2 for futility. So slightly more aggressive for stopping for futility. And then the boundary in terms of how much alpha we want to have spent is specified by this function, with an exception that if gamma is 0, which lead to a divide by 0 here, then we just simply have it linear. And alpha in here is the required overall alpha, and T is the proportion of sample size that we reach at each interim. And F is going to return the cumulative alpha spend at T. I think we have some graphs. So here are the graphs in our plan of those two boundaries with this setup of 4 interims equally spaced. And this is the Huangshi-Dikani amount of alpha spent at each interim with a gamma of -4. And here is the amount of, in this case, beta, because it's the futility boundary spent with a gamma equal to -2. So you can, as you can see, a little bit more aggressive, more stopping at the early interims than the under the null. Sorry, than for success under the null. And our plan also will tell us what the boundaries are and what the sample size should be. So we've got this 52 per arm per stage is the full size of the trial. These would be our p-value cutoffs at the interim, and you can see our final evaluation has to be against 0.022 to adjust for the alpha spent at the earlier interims. And it gives us an expected average sample size of about 225 under the null and about 290 under the alternate, with a maximum sample size of about 440. So we can enter that into facts. So I'll just show you this in facts very quickly. I won't show you me entering it to save time. I'll show you one I prepared earlier. And hopefully you can now see my fact screen. And you can see I'm using a facts core design with a continuous endpoint. I've enabled adaptive features. We're going to recruit continuously, set the maximum number of subjects to 416. That's 52 per arm per stage. Higher responses improvement. And the time to the final endpoint is 12 weeks. We've just got the two arms, control and our treatment arm. And I've looked at 4 scenarios, but the principal one, of course, is the null and the response of one endpoint. But I've also put in scenarios at a slightly reduced effect size, 1.8, and a slightly improved effect size of 1.2. We're going to assume accrual is 4 per week, so it's going to take us about 2 years to fully accrue this trial. I've not simulated any dropouts, and the only quantity of interest we have is the p-value, and our decision quantity is the p-value at dose 1. So our Bayesian design doesn't really matter because we're just using the p-value. We're not using any. We've disabled the alternate frequentist analysis. We're simply doing one-to-one allocation, and I'm doing the interims by subjects complete. And I've got them equally spaced throughout the trial, 104, 208, 312. And then on the success futility criteria, I've plugged in the p-value boundaries that I've read off of our plan. So at interim 1, we stop for success if the p-value is less than 0.008, and we stop for futility if it's greater than 0.0736. And then we have the values for the second interim, the third interim, and then the final comparison to 0.022. And then we can run 10,000 simulations, and you can see that indeed we have controlled Teichmann error below 0.025, and we've got a power of about 90%, just that's a fraction less. And so comparing that to our plan, initially it looks like the fact simulations are have given us quite significantly larger expected sample sizes. Under the null, it's 269 instead of 225, and 329 instead of 289. But that's because our plan is not including what in some places is called the overrun, the subjects who've been enrolled but not completed. And as we have an time to endpoint of 12 weeks and an accrual rate of 4 per week, that means we expect roughly on average to have an additional 48 subjects at any interim who haven't been included in the in our plan's estimate of the sample size. That gives us slightly higher figures and facts, but that's because in those few cases where in our plan it's actually gone out to the maximum, then of course we shouldn't be adding the 48, which is why these numbers are perhaps a little bit end up being a little bit large. So if you want to estimate overrun, you need a tool which can actually do it properly. So now can we use my R code to do something similar with a Bayesian endpoint? So I keep the final success value as P, should be an O in there, of course, that should be 0.022. And we're going to add, instead of testing p-values at the interims, we're going to test Bayesian predictive probabilities of success. And we'll have a Bayesian probability of success at full enrollment and a Bayesian probability of success at current enrollment. And those, the probability of success at full enrollment will be used for stopping for futility. If the probability of success, even if we go all the way to the end, is sufficiently low, then we'll stop for futility now. And we'll add, whereas the probability of success at current enrollment, we'll use that to stop enrolling at this point, and then follow up the enrolled but not complete subjects, and then do our p-value test. So initially, I changed the facts file to add these quantities of interest in. I stop the early, remove the early stopping at the interims. I run 10,000 simulations with 10,000 weak files. I aggregate the results and load them into R. And then what I'm going to do is I'm going to extract 4 data sets. So we extract the null success quantities of interest, the null futility quantities of interest. This is because I'm using different quantities of interest for success and futility. And then we do the same for the alternate. I've also, of course, got weeks files from all the scenarios. So I for the null values, I want to limit them to scenario 1, and from the alternate, I limit them to scenario 3. And then, as well as the predicted probability values at interims 1, 2, and 3, I want the value of the final p value for the last interim, because we need to, for controlling time and error, we need to check what the threshold for the p-value needs to be at the final analysis. So the first thing we need to do is to get to where the simulation results are. So I've got my my Goldilocks continuous with no early stopping results. And that's where my folder will be. And if we look in that folder, the aggregated weeks files are called ag Goldie continuous Goldie stopping _ weeks.csv. So I copy my read facts file function, which you get whenever you do load into R from facts. And then we want to read that file in. That's going to take a while with 40,000 rows. There we go. So it's our, sorry, 1,600 rows. Sorry, 160,000 rows, because yeah, it's 4 rows per, there's a row per interim, not just a row per simulation. So we're going to, here's my file with my a function in. And here's my example code. Here we go. So I tell it scenario one. I give it, this is the name of the quantity of interest for my first predicted probability. And here's the name of the quantity of interest for the p-value. And we can see those in the, need to open the quantity of interest file. Okay, we can see the short name there. We can see the names actually in the weeks if we look at the weeks file. The p-values are all at the end. They're the last columns. So we have quantity of interest 2_1 at the maximum probability, and quantity of interest 2_2. The first number tells us what type of quantity of interest it is. The type 1 are the posterior probabilities, type 2 predictive, type 3 p-values. And then number 1 is the current enrollment. So that's the stopping for success. And quantity of interest 2 is the predicted probability at trial maximum, which we use for stopping for futility. So I get my 4 sets of quantities of interest. And then I call my function, which is going to, I need to take some hashes out of here. Now I've got a little function that evaluates the Huang-Shi-Dikani boundary family. I could tell it how many interims there are and what the family parameter is, the -2 and the -4 and the -2. And for my purposes, I don't want the cumulative type 1 error spend. I want the individual type 1 error spend at each interim. I tell it my required type 1 error, 0.025. One of the slight differences with doing compared to a group sequential is that we're doing this with a fixed sample size. In a group sequential, it adjusts the maximum sample size to achieve the power. We can't do that here. So what I tell it is how much type 2 error it can spend over the interims, and the rest it'll retain to the final analysis. We run that, and lo and behold, we have some thresholds. So what it's outputting is six lots of numbers. So the first 2 are the thresholds. The first one, the stopping for success. The second set are stopping for futility. It doesn't bother to calculate the p-value. We've got the p-value we need to use there. And then it says, and for that set of simulations. This is how many simulations in the null stop for futility, in the null stop for success. So you can see we're less than 0.025. This is from the alternate, how many stop for futility. So again, you can see we're less than 0.1, and this is how many stop at each point for success. So we're going to get a reasonable amount of early stopping, both for success and futility, and we should have control of time and error and power. And so we plug those bounds into a fax file. And get our simulation results. Apologies, I've overrun time a little bit, but I will carry on. But I will skip with the demonstrations and just stick to the slides now and get through the rest a little bit more quickly. So that's what we've just seen. So these are the results. That's the threshold results that came out. You'll notice there's a slight problem, which is that it wants us to use different final threshold. Instead of 0.022, it wants to use 0.0194. And of course, our predicted probabilities are calculated, including telling it what the level of the final test will be. So these thresholds are set for predicted probabilities when the final p-value is 0.022, but now it's telling us we need to use a slightly lower threshold. So we could iterate. We could say, okay, well, let's put 0194 in, run without the threshold stopping, and repeat what I've just done. That actually then yields a final test of about 0.0198, and so on. So it could. I'm not sure how well it will converge, but actually it turns out that the results, just plugging these in, so using these thresholds, even though the predicted probabilities for a slightly different level alpha at the end, it all works out. The sample size is a little bit higher, 290 and 337, but you can see our power and type 1 error are controlled correctly. So one of the advantages of using the Bayesian predicted probabilities is that unlike the p-values, we've actually got a pretty straightforward way of taking into account the missing data, the data from the incomplete subjects. So let's assume that our endpoint that's seen at 12 weeks, and we can also see at 4 weeks and 8 weeks. And let's, just for sake of argument, assume that for this particular endpoint, we see the full response at the first visit, but there's just some noise in it. And we're going to use this function to generate the visit data, where ft is going to be set to 1 for all t. We have this is the mean for the dose that the subject's on. This is a subject-dependent error term. So this gives rise to the inter-subject variability, and then we have the sort of per observation error term. And I've simply split the overall variance 50-50 between those two. So we've got a standard deviation of 3 in the overall endpoint, so a variance of 9. So we'll have a variance of 4.5 for this term and a variance of 4.5 for this term. So effectively, they'll have standard deviations of about just over 2. And we're going to use a very simple longitudinal model, the linear regression. and that just fits an observation. So for any subject, we fit the latest, most recent observation we have, and we take the linear relationship between that and the final endpoint, which we estimate by looking at the patients for which we have complete data. And we put some relatively uninformative priors on the linear intercept and the slope, and on the noise term. And then, of course, we have to repeat the process because now they'll have different boundaries. So we go back into running 10,000 simulations with a longitudinal model. Now, in informing the predicted probability estimates, we get some stopping criteria out of that. And we plug those in, and now we have a Goldilocks with longitudinal model version. And while we haven't reduced the sample size under the null to quite back to the levels, we've reduced it compared to the Goldilocks without longitudinal model, but not so much. We haven't got it back to the levels that we had with the group sequential design. But for the alternate, we have. So we've now got a lower expected sample size. Now we're never going to reduce it by that much. Number of subjects with that endpoint is about 48, and of course we're imputing their final endpoint. So it would be surprising to have an effective sample size of more than about 24, which is so we're actually seeing almost exactly that in the alternate. So we reduced the sample size down to 314. We've retained the power and the type 1 error control. And just to note, for those of you, if you're not FACS licensees, FACS is free for academic and government institutions, and there's if you're a commercial organization and you want to evaluate FACS, there's a free evaluation license for all of FACS. It's not limited in any way, except in duration, where you can get it for about 3 months. So if you'd like to be on our webinar mailing list, do email me at Berry Consultants. So I hope that's been of interest. Thank you very much. Any questions come in over the talk? Doesn't look like it. Okay. Thank you very much, everybody. Hope to see you again next month.